Welcome to this lesson on optimization problems in calculus. Today, we're going to tackle a challenging but practical optimization problem about designing a cylindrical water container with minimum cost. Here is the problem. You are the member of the Innovation Club and you are tasked with designing a cylindrical water container that holds exactly 1000 cubic centimeters or 1 liter of water. Your goal is to minimize the material cost while still meeting the volume requirement. The bottle must be constructed with 3 different materials. First, the side material for the curved surface costs 3 ringgit per square centimeter, but it only works effectively when the height of the bottle is at least 15 centimeters. Second, the top material costs 1 ringgit 50 cent per square centimeter and is limited to a maximum radius of 8 centimeters. Third, the bottom material costs 2 ringgit per square centimeter and must be made of a thicker material that requires the radius to be at least 4 centimeters. The question is, what radius and height should the container have to minimize the material cost while still holding 1 liter considering the constraints on the height and radius of the container and the cost of the different materials? Let's approach this step by step. First, we need to define our variable and formulate our objective function. Let's denote the radius of the cylindrical container as r measured in centimeters and the height as h measured in centimeters. Since the volume is fixed at 1000 cubic centimeters, we have this volume constraint, v equal to pi r square h equal to 1000 centimeters. Let's formulate our cost function. The total cost C is the sum of the cost for the side top and bottom materials. For the side, the area is 2 pi r h and the cost rate is 3 ringgit per square centimeter, giving a cost of 3 times 2 pi r h, which equals to 6 pi r h. For the top, the area is pi r squared and the cost rate is 1 ringgit 50 cent per square centimeter, giving a cost of 1.5 times pi r squared. For the bottom, the area is also pi r squared, but the cost rate is 2 ringgit per square centimeter, giving a cost of 2 times pi r squared. Adding this up, our total cost function is C equals 6 pi r h plus 3.5 pi r squared. Let's consider the constraints and simplify our problem. We have these constraints. The height must be at least 15 cm. The radius must be at most 8 cm for the top material. The radius must be at least 4 cm for the bottom material. To simplify our problem, let's express h in terms of r using the volume constraints. Since v equals pi r squared, h equals 1000, we can solve for h to get h equals 1000 divided by pi r squared. Substituting this into our cost function, we get c equals 6 pi r times 1000 divided by pi r squared plus 3.5 pi r squared. This simplifies to c equals 6000 divided by r plus 3.5 pi r squared.
Now let's consider the minimum height constraint. Since h equals to 1000 divided by pi r squared must be at least 15, we get 1000 divided by pi r squared is greater than or equal to 15. Solving this inequality, 1000 is greater than or equal to 15 pi r squared. R squared is less than or equal to 1000 divided by 15 pi. R squared is less than or equal to 200 divided by 3 pi. R is less than or equal to the square root of 200 divided by 3 pi. R is less than or equal to approximately 4.61. Combining this with our other constraint, 4 is less than or equal to R is less than or equal to 4.61. So our feasible region for R is now this interval. Since we have a closed interval for R, we need to check the cost function at the endpoints of our feasible region. Our cost function is C equals to 6000 divided by R plus 3.5 pi R squared. At R equals to 4, C of 4 equals to 6000 divided by 4 plus 3.5 pi times 4 squared. C of 4 equals to 1500 plus 56 pi. C of 4 equals to 1676 ringgit. Minimum. At R equals to 4.61, C of 4.61 equals to 6000 divided by 4.61 plus 3.5 pi times 4.61 squared. C of 4.61 equals to approximately 1302 plus 233. C of 4.61 equals to approximately 1535 ringgit. Comparing these two values, we can see that the cost is lower at R equals to 4.61 centimeters. Now, let's calculate the corresponding height. H equals to 1000 divided by pi times 4.61 squared. H equals to 1000 divided by pi times 21.25. H equals to 1000 divided by 66.77. H equals to approximately 15 centimeters. Therefore, our final answer is the cylindrical container should have a radius of 4.61 centimeters and a height of 15 centimeters to minimize the material cost when holding 1 liter and meeting all constraints. The minimum cost is approximately 1535 ringgit. Let's reflect on why the solution makes sense intuitively. The minimum height constraint of 15 centimeters was the binding constraint here. This means that if we could have gone with a shorter height, we could have achieved an even lower cost. But since we couldn't go below 15 centimeters, we had to find the optimal radius for that specific height. There is a trade-off between the radius and the height. When the radius increases, the side area 2 pi or h increases, but the height would decrease to maintain the same volume. Overall, a larger radius leads to more material for the top and bottom, but less for the sides. That's about as tall as it is wide, 15 centimeters height versus approximately 9.2 centimeters diameter. This balanced shape minimizes the total surface area given our constraint and the different cost of materials. To summarize, we've solved an optimization problem with multiple constraints by 1. Formulating the objective function, cost function. 2. Identifying the constraint. 3. Expressing one variable in terms of the other. 4. Finding the feasible region. 5. Checking the endpoints of the feasible region. And 6. Determining the cost minimum design. This approach can be applied to many real-world optimization problems in engineering, business, and other fields.